Thank you very much, Karen, for the kind introduction. And as Karen mentioned, I've actually been invited today to give a tutorial on artificial spin ice. And I scratched my head a little bit and thought, how can I make this somehow link to this workshop? So I've added the elements of control for computation. I should point out that I have an hour for this tutorial, but I've planned to talk for 45 minutes. So feel free to ask questions at any time. We even have a coffee break, so we're really relaxed. And I'm really happy to take questions, and I encourage discussion. So I think I should start at the beginning. Where does the name artificial spin ice come from? Sorry. And this is a slide that shows you how you get from water ice to artificial spin ice. And the name, actually, spin ice, came from a paper by Mark Harris and Steve Bramwell back in 1997, where they observed a geometrical frustration in one of the rare earth titanate pyrochlores. And geometrical frustration means that you can't satisfy all interactions simultaneously. And this takes place in water ice, and because of an incompatibility of the bonding distances, you actually get two protons that sit closer to the oxygen ion and two that sit further away. And this was then mimicked in the spin ice by two spins pointing in and two spins pointing out at a tetrahedron. So this is the lowest energy state. It's referred to as the ice rule and comes about because of the crystal field forcing the spins to point along the 1-1-1 direction and the interaction between the spins. Now, it was in, I should point out actually that frustration occurs in a number of materials. So you can see it in protein folding, liquid crystals, dibulk copolymers, ferrofluids, and interesting for this workshop, neural networks. I should also point out that the tetrahedra are part of a much larger crystal. So in order to obey the ice rule in a large array of these tetrahedron, you need a large number of equivalent states. So this brings me to another phenomenon that occurs in highly frustrated systems. You have a large degeneracy of low energy states, so many low energy states with similar energies. Now, it was in 2006 that Peter Schiffer and his group came up with the idea of mimicking this three-dimensional arrangement of spins in the spin ice with a two-dimensional arrangement of nanomagnets. These are single-domain nanomagnets, so each magnet is associated with a moment represented by an arrow. And out of 4 nanomagnet vertex, you can see that the ice rule is again obeyed, 2 moments pointing in, 2 moments pointing out. This is the lowest energy configuration. But there is a problem, and that problem is that the interactions between the magnets at a vertex are no longer equivalent. So 2 of the magnets sit closer together than the other 2 at the vertex, and they have different orientations with respect to each other. So one way to get around this is actually to go to this arrangement of nanomagnets where all the interactions are equivalent. And to get here, you start with the Kagome lattice and arrange your elongated magnets. Arrange your elongated magnets onto the Kagome lattice. And these are then the configurations that you can get. This is the ice rule for the artificial Kagome spin ice with 2 moments pointing in and 1 moment pointing out. And if I zoom in here, you can see that the system is indeed frustrated because while I have 2 satisfied interactions with the red and blue arrows, 2 of the arrows, the 2 red arrows, are pointing head to head, so the interaction is not satisfied. And I can break this complicated array into individual building blocks, building up from a single ring to a double ring to a triple ring, with increasing numbers of these frustrated vertices. Now, this is how we manufacture them with electron beam lithography. They can be made from simple ferromagnetic thin film materials, here permalloy or cobalt. Typical sizes are widths of about 200 nanometers, lengths of about 500 nanometers, thicknesses between 3 and 40 nanometers. And we've also made much smaller nanomagnets, so going down to 30 by 60 by 90 nanometers. So you can make them at different sizes. And you can image the magnetic states with microscopy techniques. This is actually photoemission electron microscopy taken at a synchrotron light source. And if the moments are pointing towards the left, they appear bright, and if they're pointing towards the right, they appear dark. So these two rings, Kagome rings, actually are sitting in the vortex state, so this is the lowest energy state, with all moments pointing head to tail around the ring. So one clockwise, one anti-clockwise. And if I take a double ring structure, then the lowest energy state is two vortices, one clockwise and one anti-clockwise. And the next highest energy state is called is what we refer to as an external flux closure state, with all moments pointing head to tail around the outside of the structure. And the moment on the central magnet, this one here, can point in one of two directions. Now I should point out here, it looks like one of the magnets has disappeared, but actually the moment is fluctuating, and I'll come back to that in a minute. In a triple ring structure, it also forms a double vortex state as the lowest energy configuration. But the third ring can't quite form a vortex because it shares nanomagnets with each of the two rings. The next highest energy state is also something called an external flux closure state, with the moments pointing head to tail around the outside of the structure. And in the middle, the moments can point in any direction as long as the ice rule is obeyed. So those are the lowest energy states. Now, in recent years, people have been interested in systems with superparamagnetic islands. That means that the moments are free to fluctuate backwards and forwards. So each nanomagnet has two states. And in order to look at these, we came up with an idea of looking at a wedge sample so that you can easily find the sweet spot in your microscope where these moments are fluctuating at the time scale of the imaging technique. And so at the low energy, at the low thickness end of the wedge, the moments are fluctuating in a collective manner. And if you focus, for example, on this structure here, actually the structure is fluctuating between these low energy configurations. If I go to a slightly thicker wedge, part of the wedge, then you see that the moments are no longer fluctuating, but the structures are in the lowest energy configuration. So actually, they're not fluctuating on the time scale of the measurement, but they are fluctuating very slowly. So between the time of making the sample and bringing it to the microscope, the moments have fluctuated, and each structure has relaxed into the lowest energy state. Now, at the very thick end of the wedge, the moments are frozen, so these structures haven't actually found their way to the lowest energy configuration. Okay, so that was the introduction. I now move to my first topic, and that is emergent magnetic monopoles in artificial spin ice. And to show you what I mean, I start with a schematic. This is an array, an artificial Kagome spin ice. And if I apply a magnetic field towards the left, then all moments will point towards the left. If I apply a field towards the right, that you actually get reversal via these chains of reversed moments, something that we refer to as Dirac strings. And if one takes a closer look, one finds that there are actually charges at each end of the strings, one positive and one negative charge, something that we refer to as a monopole-anti-monopole pair. And let me just show you in detail how this works. So here is my array with all moments pointing towards the left. And I take motivation from a paper by Castelnova, Mesner, and Sundi back in 2008. And the idea was to take a dipole and stretch it into a charged dumbbell. And so I can replace each of these moments with a charged dumbbell, so that at a vertex, I have, for example, two negative charges and one positive charge, so a net positive charge. And at the other vertex, I have two positive charges and one negative charge, so a net positive charge. And so I have all these negative and positive charges on alternating vertices on this array. And if I apply now a field, I can reverse a string of moments. And I find that the charge stays the same everywhere, except at the ends of the array where I have this negative and positive charge. And if you look closely, you'll see that the charge has actually changed from plus 1Q to minus 1Q. So there is a change of minus 2Q. And here, there is a change in charge of plus 2Q. So this gives me a definition to go and find these emergent magnetic monopoles in my array. So
sorry.
now,
Can I
yes.
ask maybe a silly question, but the divergence of the magnetic field is not different than zero, so why do you call them magnetic monopoles? These are not magnetic monopoles, right? Electromagnetics remains the same.
Yes, this is actually in the framework of the Dirac monopoles, and in Dirac's explanation to take into account Maxwell's equation, he actually considered an arbitrary narrow flux tube between the monopole and antimonopole to take care of the fact that the magnetic flux should be conserved.
Which means that if I do the write down the Maxwell's equations here, I would have that the divergence of the magnetic field is not zero?
No, it is zero. So div B equals zero. Yeah. Yeah. So it's not. It's an emergent magnetic monopole that emerges out of the collective behavior of the spins, but it's not a monopole, a single magnetic charge in free space, as in the framework of particle physics. Okay. Okay, so let's go to the experiment. So here is my array. I apply a field towards the left, reverse the field, and then my magnets will have their moments pointing towards the right. Let me just reset that and show you what the image looks like. Now I apply a small field, and I see my reversal via these strings. On the right-hand side, you can see what the image looks like. And I can then map using my definition where the monopoles are. I can also look at the smeared charge density, and I find that really I have charges at the ends of these strings. And I can watch then during magnetization reversal how these monopole-antimonopole pairs nucleate and spread through the system. Okay, so that was the artificial Kugami spin ice. One question is, how can I control these Dirac string avalanches? And what I can do to my array is change the shape of the nanomagnet. So, for example, I can make this magnet a little bit wider, so it'll be the first magnet to switch. And I can make so that it switches in the field. I can make this magnet a little bit narrower, so that when an avalanche meets it, like here, then it will stop at this magnet. And this shows some experimental proof of that. So here is my array. Here are my start magnets. I apply a field. My avalanches start here. And here are my stop magnets. And when the avalanches spread, then they stop at these stop magnets. So this is a brief way to show that you can control what happens in these arrays by changing the shape of the magnets. Now, interestingly, this is what happens in a thermally active system. So now the moments are free to fluctuate, but in a collective manner. And actually not very much happens. So it appears like these antimonopole pairs are confined. And one can explain this by looking at the local energetics. So here is arrows representing my magnets. And when I flip one of these magnets, there is a small change in energy. But if I flip another magnet, then there's a much larger change in energy. And not only that, there is actually quite a high energy barrier to do this. So essentially, energetically, the monopole-antimonopole pair like to remain confined. And this is very different in the square ice. In the square ice, so this is again a thermally active system, I can use a field to set the moment orientation to point to the bottom left. And then I can remove the field and allow the system to relax. So this is now happening spontaneously. And here, the the defect pairs are nucleating and spreading through the system. This is something we refer to as the string regime. And these eventually coalesce to form domains separated by a domain boundary. And I can understand these domains by looking at a single square plaquette. You can see here again, the lowest energy configuration is all moments pointing head to tail. So I have a chiral state here with an anti-clockwise chirality. I can add another plaquette with the opposite chirality, and I can continue to add these plaquettes. But this is one of two degenerate states, so I can simply reverse the chirality to give the other domain. And as I said, these are separated by domain boundaries. But these domain boundaries cost energy. So eventually, if I leave the system to relax fully, these domain boundaries will anneal out until I get a fully ordered low energy state. So I don't, in this particular case, I don't need a computer to tell me what the ground state is, although it's fairly obvious. These thermally active systems provide a route to the ground state, so essentially do it for themselves. Now, that was the square ice. It's worth now to talk about the naming of the types, or the vertex types, so the different configurations at the vertices. And these are labeled type 1 to type 4. Type 4 is the highest energy state, so with all moments pointing out or all moments pointing in. This is highly energetically unfavorable, so you don't usually see this in the experiment, so let me just get rid of those. The next lowest energy state are the type 3 vertices. These have a charge associated with them, plus or minus 2q. And then the lowest energy configurations are the type 1 or the type 2 states. These have 2 moments in and 2 moments pointing out at a vertex. And, but they are not completely degenerate. The type 2 vertices have a slightly higher energy, and that's because 2 of the moments, or 2 pairs of the moments, are actually pointing head to head or tail to tail. And they're actually associated here with a direction. And the emergent magnetic monopoles are actually the charge above the ground state. So in the Kagome ice, you have alternate charges on a vertex. In this case, the lowest energy state is 0 charge at every vertex. So essentially, the reference state is q equals 0, and so the delta q is essentially can be mapped onto the q. So it's the same as the charge. Okay, so those are the different types, and then it's quite interesting to consider if you have defects moving apart on a charged background. So I showed you these type 1 chains on a type 2 background. Then you can see that the energy goes down. So naturally in such a system, the defect charge pair forms and then separates. If you have a type 2 chain on a type 1 background, then this pair might form, but it's very energetically unfavorable for this charge pair to separate. So they actually come back together again and immediately annihilate. So it's unlikely then that you will see it. This is actually the type 1 chain on a type 2 background, and this is the type 2 chain on a type 1 background. Okay, and just a few more words about the square ice, some work from other people. This is actually from Elena Vedmedenko, and it's kind of nice because it shows how you can store energy in such a square ice array. And she's actually mimicked this with a macroscopic array of magnets. And essentially by putting a magnet at the right-hand end like this, then she sets one of the magnets, and then she can essentially twist or turn the other magnets using this magnetic rod. But because it's unfavorable, when she moves the magnetic field, these then switch back. So, like this. So it's kind of nice. It's a way actually of storing energy in these arrays. And the other thing that I should mention, another idea for control, is to actually use heat at the borders of the array to cause these charge defects to nucleate and spread through the system from a particular direction. This is quite a nice piece of work from Alejandro Leon. Okay, so this is a picture then of this lowest energy ground state. So we weren't the first to observe it. We were the first to observe the relaxation in real time, but this was the first image from the group of Chris Marrows. And the reason that these ground state domains form at all is because the system is not, does not have these highly degenerate ground states. And the reason for that is what I mentioned before, that the interactions between the magnets at a vertex are not equivalent. So one way to get around this is actually to raise one sublattice compared to the other. And in this way, you go to you have a highly degenerate low energy state, and you get something that's referred to as the Coulomb phase, where you can have actually monopoles freely moving against a fluctuating background. So there's a lot of interesting physics here. So that's all I want to say about emergent magnetic monopoles. Now, just a few words towards bio-inspired computation. And the idea, at least from what I gather from the some of the other talks at this workshop, is that you need some kind of complex system. So I just want to highlight that these systems are complex. Of course, you also need to be able to input information, compute, and have some output of information. So let me start with our first steps towards computation. And we started by thinking about nanomagnetic logic. And I'm guessing, although I didn't see the talk, that Wolfgang Porag talked about this work on nanomagnetic logic, where you have an input and two outputs. And the other idea is somehow to transfer information along a chain of magnets, where the magnet on the left-hand side in yellow is the input, and the magnet on the right-hand side is the output, highlighted in green. And so if the input magnet moment is pointing towards the right, then it will set its neighboring magnet. These will like to align themselves antiferromagnetically, and the output magnet is then set. And if you reverse the input magnet, then you reverse the output magnet. But the problem is that this is prone to errors, and if you have errors, that's, I guess, not a good thing. So we thought about what if you could actually take some inspiration from the artificial square ice and make this kind of arrangement with a chain of square rings. And this shows an image of that chain. So actually what we find is that there are no defects. We can make chains up to 19 rings. Here also no defects. And as you already saw from my results from the square ice, my guess is that you could make an arbitrarily long chain and you would still have no defects. And this is how we do it, actually. We initialize the array with a magnetic field, use this thermal relaxation, so heat the system so that it thermally relaxes, and then measure the output by imaging. So here is our first logic gate. The two inputs are indicated in yellow. The output is indicated in green. And this is the map of errors for that gate. So each of these pixels corresponds to 11 logic gates. These are just the rows and the columns of the arrays. And thickness is changing from the right to the left. And the number of gate failures is 0 when this color is blue. And so apart from in the very thin region where the magnetic moments are still fluctuating, and the very thick moments, the very thick film where the magnetic moments are frozen, you can see that we actually have a very good output or very good success rate in terms of gate failures. They're practically 0 everywhere except perhaps in this region, but we guess this is something to do with an artifact in the nanofabrication. So that was the real experiment. But if we make the calculation, we find that actually it's predicted that these gates will only work for the 0, 0 and the 1, 1 inputs, and only for a small range of temperature. So to get around this, actually we needed to add a bias island here. And in this way then you can actually have successful functioning of your logic gates for a wide range of temperature and for all inputs, as you would expect. Now I should point out, that I'm not the only one, or our group is not the only one working on nanomagnetic logic. There are, with artificial spin ice, there are other groups. And this is an example from Bartel van Weyenberger's group, where they use the fact that you have many ground states, and they use the fact that the ground states corresponding to all input states have the same energy. So rather than considering individual configurations, they're now interested in the energy levels and the general configurations. There's also a paper here on computation in artificial spin ice. So people are just beginning to think now, how can I compute using these complex arrays of dipolar coupled nanomagnets? Okay, so that was a little bit about computation. And I want to just say a few words about complexity, just in case you didn't think these systems were complex enough. I turn to a network graph, and some of you will know that if I take a single nanomagnet with two states, I can represent these two states with two dots joined by a line. And if I add another magnet, then I have 2 to the 2, so 4 possible states, which I can represent as a square. If I add another magnet, then I get 2 to the 3 for 3 magnets, 8 possible states, so I have a cube. And I can go on to 6 magnets, so I have now 64 possible states, and this is something referred to as a 6-dimensional hypercube. And if I go down to 2 rings, I'll have more than 2,000 possible states. And if I have 3 rings, then I have almost 33,000 possible states. So I have a sufficient number of states even in 3 rings, in a 3-ring structure. And this is actually the single ring structure, showing how you relax from one state to the other. And here we've just chosen the low dipolar energy subnetwork. And these 6 states in the middle, these correspond to all moments pointing towards a given direction, given by the orange arrow. And there are 6 possibilities, hence the 6 red dots. And the lowest energy states are these vortex states, clockwise and anti-clockwise, indicated by the blue dots. So we can set one of these states with a magnetic field and then watch with microscopy how this step-by-step with single island switching goes to the vortex state. And if I heat this single ring structure, then I can watch how this ring flips between the 2 vortex states. So here is actually a video of that. So here you see the flipping between the clockwise and anti-clockwise vortex states. If I go to the double ring structure, then I can see that there are 2 states that are separated by a single island flip. And this is actually the central moment that is flipping backwards and forwards. And if I turn now to the movie of this happening, then what you'll see is that the central island moment flips rapidly because the ice rule is maintained. But around the outside, there are collective events of the moments flipping. So just start that. Okay, so in the center, you see these rapid fluctuations, but around the outside, there are collective switching events that happen more rarely. Now, in the triple ring structure, there are more of these low energy states that are connected by single spin flips. And that's because, essentially, these are the spin flips in the center of the structure where a single spin flip doesn't break the ice rule. And so now in the video, you will see rapid fluctuations in the center of the structure, and around the outside again, these collective switching events. So that was the network diagram, the network energy diagram. But of course, one needs to also consider the energy levels. So this is actually dipolar energy calculation for a single ring. And at the lowest energy, so the ground states, as I mentioned, was this these vortex states, clockwise and anti-clockwise. And the highest energy state has all moments pointing head to tail. And then there are different states at intermediate energy levels. So I think one question is, how can I access these different energy levels in such an array? And this is one example from Bob Stamm's group with Zoe Budrikis and Paolo Politti. And the idea here is that you have a set of nanomagnets, and if you apply a field, for example, towards the right, then all the magnetic moments will point towards the right. And then if you apply a field towards the left, some of the magnets will switch, and then further of the magnets will switch. And you can represent this then by this kind of graph where a dot corresponds to a configuration of the element spins, and the line corresponds to the orientation of the field the field here has a fixed magnitude, which is very similar to the switching field. And this field is just large enough so that you can access these 4 configurations. But if one then makes a control magnet, so if you can actually control the spin in one of these magnets, it's actually possible to access 128 of these configurations in a graph that looks like this. Okay, so that was a small word about complexity. Now a word about accessing these states, and there are various means to access the states. One possibility is to turn to multiferroic composites, or these are also referred to as artificial multiferroics. And the idea here is that you take a ferroelectric material combined with a ferromagnet, apply an electric field to the ferroelectric so it changes shape, and this strain is then transferred to the ferromagnet so that it changes its state. And here I have an example of nickel nanoislands on a PMNPT substrate. This was actually a collaboration with Greg Carman and Fritjof Nolting and their groups. And this is actually the array taken with, it's an image actually of the magnetic configurations taken with photoemission electron microscopy. And essentially these are ellipses, 200 by 100 nanometers in size. If the nanomagnets appear dark, then the moments are pointing towards the right. If they appear bright, then the moments are pointing towards the left. And if I apply an electric field, then what I find is that it looks like some of the magnets have disappeared, but actually what's happened is the magnetization has rotated. And if I continue to increase the electric field, then they relax again. So if I look, for example, at this magnet, then the magnetization is pointing to the right, rotating by 90 degrees, and then relaxing back to point to the right. If I, pointing to the left, my right. And if I then look at this magnet, the magnetization is now really pointing towards the right, rotating by 90 degrees, and then flipping over to point to the left. So this just shows a first demonstration of how you can control the input states with an electric field. And actually Greg Carman has recently, and his group have recently published a paper where they show the control of the flipping of a single magnet in an artificial Kagome spin ice array using an electric field. Another way to write states into these artificial spin ice structures is with an MFM tip. So this shows a very nice example that was published in Science in 2016. And the idea is to take a global field to essentially have a background magnetic field and then approach an MFM tip towards the array so you can essentially change the states in the magnetic array. In this particular example, to write the word ice into an artificial spin ice array. It's also possible in a connected array to use an MFM tip to essentially nucleate and write domain walls into a wire. And you can see in this simulation, the domain wall is nucleated, but actually forms 2 domain walls that separate. And in this way, you can actually switch individual bars in a connected artificial Kagome spin ice array. So there are really various ways that one can control these arrays. Okay, so that's all I want to talk about in terms of computation. I now turn to chirality control. And actually, chirality occurs in a lot of magnetic systems. Here are some examples in artificial spin ice. And this is from Nicolas Rougemont and his colleagues. It was a simulation showing that if you have 3 magnets meeting at a 3 nanomagnet vertex with all moments pointing inwards, then due to a minimization of the stray field interaction, you actually have a curling, and this curling has a chirality, in this case running clockwise. And it's doubly degenerate, so you can have a curling in the other direction. It's also interesting that domain walls have a particular chirality, and depending on their chirality, these are actually transverse domain walls. If you apply a magnetic field, they will pass either to the left or to the right in a connected artificial Kagome spin ice network. This is also a kind of chirality control in the building blocks of the artificial spin ice. So, for example, in this single ring structure, you can see that the upper three nanomagnets are narrower than the lower three magnets. So it's the lower three magnets that will reverse first during magnetization reversal. And so all of these single ring structures are in an anticlockwise vortex state. And in the same way, then you can set double ring structures and also triple ring structures here in the external flux closure state. So it's possible then to engineer the design so that they fall into a particular magnetic state. Now, another thing you can do is look at dynamic chirality. And for this, I now turn to something called the chiral ice. So you start with a square ice and rotate the nanomagnets by 45 degrees. And if I take a single plaquette and add the moments and add the average magnetization direction, I can consider what happens during thermal relaxation. So it turns out that the average moment rotates by 90 degrees, and if I heat up a little bit, it continues to rotate in a clockwise direction, and we never see rotation in a counterclockwise direction. And here, so this is a kind of chiral dynamics. And if I show an image now of taken in the photoemission electron microscope, so this is an image with all moments pointing upwards, with the rotation by 90 degrees, and then with the rotation by a further 90 degrees. And here you can see the images. Now, this rotation doesn't happen in a collective manner. You can see that it happens via domains. These domains run diagonally across the image, either from top to bottom or from bottom left to top right. And I can understand this by looking at looking once again at this array and considering the stray field. So this was actually the work of Sebastian Glieger, and he performed some simulations, and when he looked at the stray field configuration, he found that there were antivortices in the stray field. And if I consider this array in a remnant state, then the antivortices form these pairs. So it's quite an ordered array of these antivortices, something that we refer to as an antivortex crystal. And during reversal, then you have these diagonal domains forming, and while in the center of the array you still have these antivortex pairs, around the outside you can see quite an asymmetric ordering of these antivortices. And it's this antisymmetric ordering, so the lowering of the stray field energy at the array edges, that causes this chiral dynamics in, so this rotation of the magnetization in a given sense. So that was chiral dynamics. Now I turn to a dynamic chirality, and this is in a vortex state, or a Landau state in a square element. This has 4 triangular domains with the magnetization indicated by the arrows. And, and in the center, the magnetization is actually pointing out of or into the board. And if I apply an oscillating magnetic field vertically, then what I find is that this central core region either precesses clockwise or counterclockwise, depending on whether it's pointing out or into, the magnetization is pointing out of or into the screen. And I can combine this in a hybrid system with a layer with an out-of-plane magnetization. So these are worm-like or stripe-like domains. And if I then look at the domain structure in the in-plane layer, I see an imprint of the stripe domain pattern in the in-plane layer. And if I look at the worm domains in the out-of-plane layer, then I find that they are actually constricted so that they run actually parallel to the borders and curl at the position of the domain walls. And the idea here then was to see that if we had this precessing vortex core, if we moved it across a domain boundary, that it would actually switch. So essentially now I have the vortex core with the magnetization pointing downwards, so this is the same direction as the magnetization in the domain below it. This is a cobalt palladium multilayer. And when it passes across the domain wall, it not only switches, but also then starts to process in the opposite direction. So now I just show you the experiment. So here you see some images of these stripe domains, and here is a map of the vortex core position. And when the vortex core is processing above a dark domain, then it processes clockwise, and when it's sitting above a bright domain, then it processes counterclockwise. And it's actually quite complex what's going on. I show you just the first steps in this process. So this is this hybrid system. It's actually a cobalt-palladium multilayer with a permalloy layer on top. So below is an out-of-plane system. This is an in-plane system. And here is the vortex core with magnetization pointing downwards. And when it approaches the boundary, actually, there are two singularities that are formed. These are something that is referred to as block points. And they look something like this. Essentially, a block point has magnetization up at the top and bottom pointing up and downwards. And then around the circumference, you can either have this hedgehog configuration, a circulating configuration, or a contra-circulating configuration. And I'll come back to block points later. But I wanted to, you're probably wondering, well, what has vortices got to do with frustration? And this is actually the work of Guido Meyer and his group. And this shows a first example where you take oscillating vortices and you actually drive them with a magnetic field. And on the right-hand side, actually, you can see the normal modes. And I have a video from his group which quite nicely shows this eigenmodes of these coupled vortices, which I actually find quite mesmerizing. So vortices in adjacent disks are coupled, and one can actually use this in a frustrated system. So now you can just about see the artificial Kagome spin ice that has now been replaced by double disk structures. And interestingly here is that the behavior is frequency dependent, and you can actually tune the frustration by changing the frequency and turn it on and off at will. Okay, so I've moved to the second to last topic. This is three-dimensional magnetic systems. And three-dimensional magnetic systems are actually interesting because of the greater degrees of freedom they give, which is interesting both for fundamental science but also for applications. And if you want to find out more about this, I point you to these two very nice review articles, and there's also going to be a talk by Amalio Fernandez Pacheco later on in this workshop. We're actually interested in imaging three-dimensional configurations and actually people have used tomographic imaging techniques to image 3D configurations before. This shows actually neutron tomography with spatial resolution from tens to 100 micrometers and sample thickness of up to millimeters. And this shows actually soft X-ray tomography and electron tomography that can image three-dimensional structures with spatial resolutions below 10 nanometers and sample thicknesses below 200 nanometers. Now, we wanted to get the best of both worlds and measure with hard X-rays sample thicknesses up to millimeters with these very low or very high spatial resolutions. And we did this using synchrotron X-ray tachography. And this was a tachographic tomography using hard X-rays. So we were essentially combining hard X-ray phase imaging with resonant elastic scattering. So what you see actually on the left-hand side is a buckyball structure created with two-photon lithography. So it's a polymer scaffold with a cobalt coating on the top. And this is not just a structural image, it has element specificity. So the blue color really corresponds to the polymer, and the orange color corresponds to the cobalt on top. And like any tomography technique, you can actually look at slices through this structure. So that's the bottom, going up through the vertices, and then up to the middle. So that was the first step, but the next step was actually to look at magnetic imaging. I should also point out that this buckyball structure is a bit like an artificial spin ice that's been wrapped round on itself, but we wanted to perform magnetic imaging, and for this we first turned to a gadolinium cobalt pillar, and this actually shows an image of that pillar. It's very, very complex, and there are people that think that one can use this very complex 3D magnetic configuration to actually store information. And this is one part of that pillar. You can see two domains with magnetization pointing up here and down here. And there are two vortex cores that are elongated in this 3D system. And one is within this domain boundary indicated by this white plane. And the other vortex core is here. And where they meet, you can see these structures. And we believe these structures actually correspond to these two block points, so the circulating and contra-circulating block points, or anti-block point. And again, because this is a tomographic image, one can look at these structures from all sides. That's the block point, and this is the anti-block point. Okay, so that's magnetic imaging in 3D. I now just come towards a few conclusions, and I always show this image basically because I like it, but mainly because it looks like a stained glass window and it's like looking through a window into the future. But I'm going to use this to just tell you a few more things that you should know about artificial spin ice. And just to show a few more examples, this is actually from Peter Schiffer's group, some work by Ian Gilbert. And the idea here is that magnetic materials can show a memory in the hysteresis. And with artificial spin ice, you can actually visualize these memory effects. So you can see that these two configurations have been obtained by going through a minor hysteresis loop, and they look very similar. Another possibility is to look at fast dynamics. So I think we will have a talk later on today about fast dynamics. And one of the interests is reconfigurable magnonic crystals, where you can transmit and process information as spin waves. And this shows examples of change in FMR absorption versus frequency for two artificial spin ice type configurations. This is from the group of Kunle Adeyeye. And this shows an example of how the spectra in an artificial square ice can be very different depending on the number of these charge defects and Dirac strings. And I should also point out that these square ice are very reminiscent of antidot arrays. Antidot arrays are thin films with arrays of holes, and if you increase the size of the holes, you get something that looks like a connected square ice. And if you look at the magnetization reversal, this looks very much like this string regime that I already showed you. And these were really one of the basic systems that were used for studying magnonics and systems that were very interesting, have been very interesting, and are still very interesting for magnonic crystals. So another thing that I should mention is that I've showed you two basic geometries, the square ice and the Kagome ice, but there are many other geometries that you can look at that all have their own unique and fascinating physics. So this is variations on the square ice, the Shaktri and the Tetris lattices. Here, the first two were the Shakti lattice, here the Tetris lattice. And here you can see that there are actually one-dimensional chains in a two-dimensional system. So the behavior is actually different in these one-dimensional chains. One can also look at artificial quasi-crystals. This is a connected quasi-crystal, or this is a separated quasi-crystal design. Again, they show some very interesting physics. Also, one can look at perpendicular systems, which is kind of interesting for spintronics. And here you can see a few small structures with perpendicular dots. These clusters are actually sitting in the lowest energy states. And in terms of scalability, sometimes people ask me, how small can you make them? And this is an example, This is an example which is from another one of the speakers at this workshop. This is RKK coupled iron atoms on a copper substrate. And one can see differences if one increases the magnetic field. So here, for example, you can see one last atom with the moment pointing in a different direction to the other 6 atoms, and then finally switches as you increase the field. So if you were going to ask, well, how small can you make them? Well, I guess the answer is if you're willing to work at 0.3 Kelvin down to the atomic scale. Just a word about sample geometry. Many of you will know that the magnetic behavior is influenced by many things. The magnet dimensions will determine whether you have a single domain or a multi-domain structure. So the smaller the magnet is, the more likely it is to be single domain. The intermagnet distance matters because there you can vary the intermagnet coupling. The material or the magnetization at saturation, the dimensions and thickness matter because this influences the energy barrier to switching and again the dipolar coupling. And in a connected network, the reversal happens via domain wall propagation. So this is a picture of the kinds of arrays that we've built in the past, and in these kinds of arrays we see these Dirac string avalanches. Here is another array. Now you can see that the magnets are much narrower. So this means that the shape anisotropy dominates over the coupling, so that if you apply a field, you can actually switch individual magnets. And this shows an MFM image where you can see that actually you have this unfavorable configurations of 3 moments pointing in or 3 moments pointing out at a vertex. So you have fully charged vertices in this array. And this shows one of these networks, again with the Dirac string avalanches, but here you can see that there is branching happening. And this is because essentially the geometry of the system, or I should say the configurations seen in the system, are very sensitive to the detailed geometry of the system. So the size and shape of the islands, whether they're connected, not connected, the thickness, etc. Okay, I just come to some last acknowledgements. I'd like to thank my group, both previous members and current members, for the contribution to everything I talked about today. I would like to thank all the people at the Paul Scherrer Institute, all of my collaborators, both the research and the technical staff, the people at the Swiss Light Source responsible for the various characterization techniques, at the Condensed Matter Theory Group, Peter Derleth, and the Laboratory for Muon Spin Spectroscopy. I'd like to thank all my international collaborators at various universities and also at various synchrotron sources. And in conclusion then, I've talked about artificial spin ice systems and also hybrid systems, which kind of all come under the umbrella of artificial ferroic systems. If you're interested to find out more, there was a review that I and Bob Stamps wrote in 2013. And just to refresh your memories then, I talked about emergent magnetic monopoles in artificial spin ice. And we've learned how to create them and how to manipulate them, but of course the next step is to build them into devices. And at least compared to the bulk spin crystals, they're more amenable because we can make these devices at room temperature. In terms of chirality control, well, I've already mentioned there are many chiral structures in magnetism. There are domain walls, vortices. I've shown you these chiral states in the Kagome and the square ice. And I've also talked about dynamic chirality, in processing vortex cores, but also in the chiral ice. And this dynamic chirality is not only interesting for computation, but may also be interesting for rotors and motors. I also talked about 3D magnetic systems, and as I mentioned, it's this added degree of freedom that's interesting both for fundamental science, but also applications. And we will continue to work on trying to manufacture these 3D systems, but also trying to measure the magnetic configurations. So the main topic of this conference is neuromorphic computing, and I showed you our first very small steps towards bio-inspired computation. As you see, we have very complex systems, and we're learning how to input to these systems and to read these systems. But there's still plenty more to do in terms of learning how to compute with these systems, in particular how to access all these different states with these multiple energy levels. But nevertheless, I'm very much looking forward in the future to seeing how artificial spin ice systems can be implemented either in Spintronics and neuromorphic computing. Thank you very much.